What we want to do now is to take advantage of data obtained from the sensors in order to know where we are located in a more accurate way. And this will be the first filter we are going to meet, the histogram filter. The histogram filter is the most straightforward solution for our localization problem. We simply divide the region of interest into n different bins or cell, and we compute the probability to be at each bin. The histogram filters also limit the accuracy to the bin's size. So if we want to increase the resolution, we need to decrease the bin's size. And a concrete example will help to clarify this. So let's imagine that our self-driving car is moving across a painted wall 5 meters long. The first meter is painted red, the second and third are painted green, and the last two are painted red. We can think of this problem as a histogram filter with 5 bins. It means that the resolution will be 1 meter. I might know that the car is next to bin number 3, for example, but I cannot say where the car is exactly. Maybe it's over here, and maybe the car is over there. It can be even on the border between bin number 3 and bin number 2, but I will consider it as being inside bin number 3. So let's assume that I have no prior knowledge whatsoever. What is the probability that the car is located next to bin 1, for example? 20%. Why? If the car must be located somewhere in this one-dimensional world, and the world is divided into 5 bins, then each bin gets 100 divided by 5, which is 20%. And if I have 20,000 bins, then I would have to divide by 20,000. Okay, let's assume that my car has a color sensor and it can detect the color of the wall next to it. If the sensor detected the color green and the sensor is 100% accurate, what will be the new probability in each bin? Now, if the sensor sensed green, then my chance to be next to a red wall, again assuming that the sensor is 100% accurate, is 0. However, the chances of being next to a green wall are 100%, but yes, we have 2 different green bins. How do I know if the car is next to bin number 2 or 3? Truth to be told, I don't know, and therefore it takes us back to what we did previously. I cannot prefer one bin over the other, and therefore the probability of bin number 2 is 50%, and the probability of bin number 3 is also 50%. By the way, I can draw the probabilities, and this drawing is called the histogram distribution, just like this. So here we have 0, 0.5, which is 50%, 0.5, 0, 0. The interesting part comes where the sensor is not 100% accurate. Why? Because in reality, sensors always contain a certain degree of noise. So let's assume that the sensor is only 90% accurate. When the car senses the color green, in 90% of the time, it will be next to a green wall, but, and it's important, in 10% of the time, it will be next to a red wall. And I can write the last sentence in a mathematical form. The probability of measuring the color green if the car is located at bin number 2 or 3 is 90%. And the probability of measuring the color green if the car is located at bin number 1, 4, and 5 is only 10%. So what do? I will show you how to compute it, and in the next video, I will show you that this solution is exactly Bayes' law. Let's start. The probability of measuring green, given that the car is in bin number 2 or 3, is 90%. But it is given the car is at bin number 2 or 3. But the initial or prior probability to be in each bin is 20%. So, just like we have already seen the law of total probability, we need to multiply. At bin number 1, we have 0.2 times 0.1, which is 0.02. At bin number 2, we have 0.2 times 0.9, which is 0.18. Bin 3 is just like bin 2. And for bin number 4 and 5, we have also 0.02. Now pay attention. The new probabilities don't sum to 1. So we need to normalize them. How do we do it? First, we need to compute their total. In our case, it is 0.02 plus 0.18 plus 0.18 plus 0.02 plus 0.02 equals 0.42. Now, we need to divide each probability by 0.42. So for B number 1, we have 0.02 divided by 0.42 equals 0.0476. This will also be the probabilities for bins number 4 and 5. And for bin number 2, we have 0.18 divided by 0.42, which equals 0.428. And this will be the same for bin number 3. So, if the sensor felt green with 90% accuracy, what will the new histogram look like? We can draw it, and it will look something like this. Over here, we have 0.0476. Bin 2 is 0.428. Bin 3 is exactly the same. And bin 4 and 5 are also 0.0476. And everything adds to 1. Great. Now, the probability to be next to a green wall is approximately 10 times bigger than the probability to be next to a red wall. And this is due or thanks to the sensor. Another important thing to bear in mind is that the sensor noise might be more complex. What do I mean? In the last example, we had 90% accuracy sensor, which means that the level of accuracy doesn't change when we sense green or red. But some sensors can be more sensitive to a specific color, so I might have a different, more complex noise model. For example, the accuracy level for red might be 90%, and the accuracy level for green might be only 80%. What does it mean? Again, that the probability that I measured red, giving that I'm at bin number 1, 4, and 5 is 90%, and the probability that I measured red, giving that I'm at bin 2 and 3, is 10% or 0.1. So far, just like before, but now we can write the following. The probability that I measured green, giving that I'm in bins 2 or 3, is 80% or 0.8. Why? Because the green sensor is less accurate than the red sensor. And the probability that I measured green, giving that I'm in bin 1, 4, and 5, is 0.2 or 20%. Now, remember that this whole thing is a recursive Bayesian process, meaning I can take the new posterior histogram and use it as a prior for the next phase. So if I sensed green and then I sensed green again, I can gain more confidence regarding the car's location. In the next video, I will show you that this very computation is exactly what we have learned in Bayes' law. Below the video, I've put some questions to make sure everything is understood. Please don't skip to the next unit until you can answer all of them. Good luck!